How could a locomotive capable of delivering nearly 2,000 horsepower from a standstill, an engineering feat that outperformed many contemporary designs, ultimately vanish from history within a decade? If you are fascinated by the hidden experiments that quietly shaped modern technology, stay with this investigation and subscribe to follow future explorations into overlooked engineering breakthroughs. Britain's railways entered the late 1940s facing a problem that could no longer be ignored. The country's vast steam fleet, once the backbone of national transport, was running out of time. Wartime coal shortages had exposed just how vulnerable the system was, and by 1947, government memoranda called for urgent action. Steam withdrawal was no longer a distant threat, it was a scheduled process, with timetables demanding new traction within a decade. Yet no single replacement stood ready. Two rival philosophies dominated the debate. The first, borrowed from America, relied on diesel engines driving generators, which then powered electric traction motors on each axle. This diesel-electric system promised flexibility and was already proving itself overseas, but it required heavy, expensive components and a complex web of electrical controls. The second approach, championed in Germany and France, used diesel engines connected to the wheels through hydraulic converters, fluid couplings that offered lighter weight and smoother power delivery. Each method brought technical trade-offs, and neither seemed a perfect fit for Britain's unique mix of steep gradients, heavy trains, and tightly scheduled services. The urgency of the crisis opened the door to radical ideas. With coal in short supply and a nationalized railway under pressure to modernize quickly, the old certainties gave way to a period of experimentation. Policy documents from the era reveal a willingness to consider almost anything that could offer reliable, high-power traction, whether through the generator motor chain of diesel-electric, the fluid drive of hydraulic transmission, or something entirely new. In this environment, the search for a locomotive that could deliver constant power from a standstill became a matter of national importance, setting the stage for unconventional solutions that would soon challenge the orthodoxies of British rail. Lieutenant Colonel L.F.R. Fell entered Britain's post-war rail crisis with a vision that challenged the status quo. Trained as a royal engineer and shaped by years in the Ministry of Transport, Fell saw the future not in copying foreign diesel designs, but in rethinking traction from first principles. His question was straightforward. Could a locomotive combine the unwavering pull of steam with the efficiency of diesel, using several smaller engines instead of one massive unit? Fell's answer was bold. He designed a locomotive powered by 4 medium-sized diesel engines, each connected through its own hydraulic clutch to a central gearbox. This setup aimed for nearly 2,000 horsepower from a standstill, with torque spread evenly across all speeds. The goal was constant, reliable power on Britain's toughest gradients, all within a modular system that simplified maintenance and offered redundancy. It was a direct response to the operational headaches that had dogged early diesel efforts. To build his prototype, Fell gathered a team of specialists. Davy Paxman supplied the 412 RPH V12 diesel engines and supercharging units. Ricardo and Comey handled thermodynamic analysis, refining the air-fuel mix under pressure from the auxiliary blowers. Shell provided high-grade diesel and laboratory testing to keep the engines running clean and cool. At Derby Works, the London Midland and Scottish Railways skilled shopmen built the chassis, crafted the custom gearbox, and integrated the hydraulic clutches and controls. By 1950, their combined expertise produced prototype number 100. More than a technical experiment, it embodied Fell's doctrine of modular torque and constant power, a machine designed to meet the urgent needs of Britain's railways. Power inside the Fell locomotive began with 4 Paxman 12 RP HV12 diesel engines, each rated at 500 horsepower. Together, they promised a headline figure just shy of 2,000 horsepower, an output that in theory could rival the heaviest steam express engines of the day. But Fell's solution to the problem of constant, reliable torque was anything but conventional. Instead of relying on a single massive engine, each Paxman unit was paired with its own oil-filled hydraulic clutch. This arrangement allowed the driver to engage or disengage any engine at will, even while the train was moving. By controlling the flow of oil, power could be blended smoothly, protecting the gearbox from shock loads and letting the locomotive match its strength to the demands of the track. Backing up the main engines were two auxiliary AEC 6-cylinder diesels, each driving a Roots blower. These supercharging units forced air into the main engines at low speeds, keeping torque high from the moment the wheels began to turn. The result was a locomotive that could, on paper, deliver nearly full power from a standstill, an answer to the age-old challenge of getting heavy trains moving on steep British gradients. All four engines fed their output through a Vulcan Sinclair epicyclic gearbox, the mechanical heart of the design. This gearbox used a series of nested planetary gears to provide four distinct ratios, automatically selected based on how many engines were engaged. The ratios ranged from 4:1 for crawling starts to direct drive at high speed. A limited slip differential split the merged power between the locomotive's driven axles, reducing the risk of wheel slip and spreading force evenly across the rails. The system's complexity was both its promise and its Achilles heel. With every component, hydraulic couplings, gear trains, differential, working in concert, the Fell aimed to deliver a flat torque curve from rest to top speed. Yet every extra part, every oil circuit and selector lever introduced new ways for things to go wrong. The real test would come not in the workshop, but out on Britain's demanding main lines, where theory would meet the realities of daily railway service. On the steep main lines of the Peak District and the Settle to Carlisle route, the Fell locomotive set out to prove that its radical design could deliver more than just theory. Test logbooks from Derby and Garsdale record a machine that, when everything worked, could outmuscle its rivals. The starting tractive effort was measured at 25,000 pounds force, enough to move heavy coal trains from rest on gradients that had stalled lesser engines. On the Settle to Carlisle, number 10,100 climbed the 1 in 80 slopes at Ice Gill with a full 400-ton consist, maintaining 30 miles per hour without a hint of wheel slip. On level track, the locomotive was clocked at 84 miles per hour, a figure confirmed by dynamometer car records and later cited in railway trade journals as a benchmark for British diesel traction. Fuel ledgers from the period tell their own story. Compared to the steam locomotives it was meant to replace, the Fell burned 25% less fuel per mile, a savings that caught the attention of railway accountants and engineers alike. Over its service life, mileage ledgers show number 10,100 racked up a cumulative 884,000 miles, a figure that stands out for a prototype. One entry, dated late 1953, notes a single driver's remark: "Never thought a diesel could pull like this uphill. Almost makes you forget it isn't steam." These achievements were not just isolated bursts of performance. On the demanding Woodhead and Ice Gill climbs, the ability to engage or disengage engines in real time gave crews a new kind of control. The locomotive's modular approach, blending 4 engines and auxiliary blowers, delivered a steady pull from rest to top speed, fulfilling Fell's promise of constant power. For a brief window, the experiment worked, not only matching the best of steam, but hinting at a new future for British mainline traction. The evidence is there in the test logs and fuel accounts the concept could work, and for a while, it did. Workshop ledgers from Derby and Garsdale read like a catalog of mounting troubles. In July 1952, a fractured gearbox bolt forced number 100 off the rails for more than a year as engineers traced the failure to a single high-stress fastener overwhelmed by a torque surge. Each return to service brought new headaches. Oil starvation in the bearings led to overheating, with maintenance logs recording repeated shutdowns and costly replacements. Hydraulic clutches designed for smooth engagement began to seize as contaminated oil caused plates to stick, cutting available power and leaving crews to juggle engines mid-run. Overheating symptoms persisted, especially on long climbs, as the cooling system struggled to keep pace. The complexity of the controls, multiple throttle levers and clutch selectors demanded constant attention from drivers, increasing fatigue and the risk of missteps. Each breakdown meant days or weeks out of service, and the repair durations stretched as bespoke parts wore out faster than they could be replaced. The evidence in the maintenance books is unambiguous. Reliability doubts were no longer theoretical. They were logged, measured, and accumulating with every mile. British Railways' modernization plan, announced in 1955, delivered a final and unambiguous verdict on the fate of experimental locomotives like the Fell. Policy documents from the Transport Commission spelled out the new priorities: standardization, fleet compatibility, and cost control. The bespoke complexity of number 100, its custom gearbox, unique clutches, and special driver training stood directly at odds with these aims. A cost-benefit memo from the board made the case plain. Maintaining a one-off machine required a dedicated supply chain, extra workshops, and drove up the per-mile repair bill. Funding for Fell's proposed second-generation design, a streamlined 2,300 horsepower machine, was withdrawn before a single part was ordered. The final blow came in October 1958, when a fire broke out in the locomotive steam heating boiler at Manchester Central. The damage was extensive, and the accident report recommended withdrawal rather than repair. By 1960, the prototype was quietly cut up for scrap, its promise undone not by engineering impossibility, but by the relentless logic of national policy. The real question isn't why the Fell locomotive vanished, but how many brilliant but complex solutions get sidelined when reliability and uniformity rule. Today, railways still face the same trade-off: bold innovation versus proven standard. The stories of forgotten experiments shape tomorrow's breakthroughs. Subscribe to uncover more hidden engineering battles.